This video will cover the second part of 4.5, definite integration by substitution. So in the last video, we looked at just regular indefinite integration by use substitution, and now we're going to look at doing the definite integration. So remember, the definite integration is when you have those limits of integration. You're actually finding a value for the integral. Before I go into the theorem here, let's go back. I'm going to do this on a separate sheet of paper. You might need to find another piece of paper to do this on. But I just want to kind of explain why doing definite integration by use substitution looks different before I actually show you the theorem for it. So if I have, let's say my function is x squared, and let's say we want to find the area under the curve of x squared from 1 to 2. Okay, so we know how to do that. That's not use substitution, but well, I'm just going to talk about graphically what's going on. So if we have the graph x squared, and let's say this is from 1 to 2, then you're finding the area of that section right there. Okay, so what happens now with use substitution? We use use substitution when we want to find the area, when we want to integrate a composition of functions. So now what if I made f be, let's find f of x minus 2. So what that means, I would have x minus 2 squared. All right, so I want to figure out what has the same area as x minus 2 squared as the integral from 1 to 2 of x squared. So if I want to take the integral of x minus 2 squared, now obviously I know that I can do this without substitution. You could just simply say x minus 2 times x minus 2. But let's think of this as from a use substitution standpoint. That is, u would equal x minus 2, and then du would equal dx. So this would look like the integral of u squared du. All right, so if I wanted to have this be the same as this, that means represent the same amount of area, then if I want the u substitution, then I would say this u squared du is the same as x squared dx, so I would find from 1 to 2. But the thing is that with this statement here, this needs to be equivalent to this statement here. So when I use use substitution with definite integration, these limits, when we're taking with respect to x here, these limits here are supposed to be x limits. Okay, so x, let's call that b, and this is x at a. So down here, with the u substitution, this is a u, and this is a u. All right, so the integral from 1 to 2 of u squared is the same thing as the integral from 1 to 2 of x squared. But now what happens if I shift this function 2 spaces to the left? So now if I take my parabola and I shift it 2 spaces to the left, we now have the parabola that looks like this. Okay, so if I shift everything 2 spaces to the left, that means that the limits of integration also need to shift. So if I want this same area, then I don't need to find the area from 1 to 2. I need to find the area from 3 to 4. Since I shifted my whole function to the right 2 spaces, then I need to shift my limits of integration 2 spaces. Okay, so that area should be the same as this area up here. All right, so if I were to use use substitution, then this would represent the integral from 3 to 4 of x minus 2 squared dx. Okay, so I kind of went backwards here with the use substitution definite integration. If this was an actual problem with use substitution definite integration, I would be given this right here. And then you would be asked to find a simpler function to calculate the area under the curve. So if this was what I was given here, let's say this is given. So I went backwards to kind of show you how this works, and now let's show if I were to give you an actual example. So if I'm giving you this, and I say find this definite integral using use substitution, then you would say, just like we said here, that u is x minus 2 and du is dx. So when I change that, you get the integral of u squared du. But then you have to change your limits of integration, because you can't say that's the integral from 3 to 4, because if you found that, that would be the integral from 3 to 4, which would be that area. Okay, if you were to find that whole area on the graph of x squared. I want it to be this area here. So that means that I have to change those limits of integration. So no longer are they 3 and 4. We have to put them in terms of u. So since we said that u is x minus 2, then what we have to calculate is, okay, what would u be when x is 3? Well, we just plug in 3 and we get 3 minus 2 is 1. So now that would be 1. And then we would calculate u at my upper limit of 4, and that would be, since u is x minus 2, that would be 4 minus 2, which is 2. So you can see that those two are equivalent area. And you can see that graphically, that when I shift 2 spaces, you have to shift the limits of integration 2 spaces as well. Okay, so hopefully graphically that helps you kind of understand what we do, what we're doing for u substitution with definite integration. Okay, so now I'm going to take all of that and look at it without an actual function, but instead with you know, the abstract part. There's no numbers here. So this is what we learned before. We have the integral of f prime of g times g prime, and that's how we use u substitution, where we make u be g of x, du be g prime of x dx. But now what we have new are the limits of integration. So you can see here how it's spelled out for you. Everything is in terms of x, including those limits of integration. But then when I make my u substitution, now I need everything in terms of u. So we talked about the f prime of u du part, but now if u is our g of x, then we need to change our u's in terms of that g. Okay? So then when we evaluate, you can see that I don't have to go back into terms of x. I can just simply evaluate like this using in terms of u. So let me show you how this works. So looking at example 1, we would do the regular u substitution like we did in the last video. So u would be the inner function 2x minus 1. Then du would be 2dx. And then we see that dx would equal half of du, but I still have this x to account for, and so that's where we have to use our, we have to solve for x. So 2x would equal u plus 1, so x would equal 1/2 of u plus 1. All right, now make all your substitutions. And also remember, these are x's, so we also have to change those in terms of u. So to change our limits of integration, we need to find u of 1. So u of 1 is 2 times 1 minus 1, which is 1, and u of 5, which is 9. So now make all of your substitutions. So this is equal to the integral, after making all our substitutions, from 1 is 1 still, to 5 is now 9. X, we said, is 1/2 u plus 1 over the square root of u, and then dx is 1/2 du. Okay. Before I take the integral now, I'm going to clean this up. So I have a 1/2 here and a 1/2 here. Both of those can come out of the integral, so they'll multiply to be 1/4. Then I need to take care of this integrand here. So u over the square root of u, I'm going to make that be u to the first divided by u to the 1/2 would be u to the 1/2. Plus, now u, or 1 over the square root of u, would be u to the negative 1/2. Okay, so that's made now all my u substitutions. Okay. So now let's go ahead and take the integral and evaluate. So I have this coefficient of 1/4, which I'm going to leave out front, so make sure to put a bracket there. And so this will be u to the 3/2, which is a coefficient of 2/3, plus u to the 1/2 with a coefficient of 2, evaluate from 1 to 9. Now here's the beautiful thing about definite integration with u substitution. You do not, like you do with the indefinite, have to replace these u's back in terms of x. You don't have to go back and now put 2x minus 1 in. If you did that, you'd have to go back and change the 1 and the 9 back to the original limits of 1 and 5. So now all you have to do is, these are in terms of u, this is in terms of u, so now you just simply evaluate. So that's what's really nice about this, is you don't have to make it go back and be more complicated. So now this would be 2/3 of 9 to the 3/2 plus 2 times 9 to the 1/2. And some of you can do this math very quickly in your head, but for sake of notes, I'm writing it all out. There we go. All right, and then let's completely simplify this. So I'm going to do this on the side, and then I'll come back after I work it all out. I'll record it. Okay, so there it is, all worked out. So hopefully that makes sense. So just remember the two things that we have to make sure to do when we have a definite integral with u substitution. The first thing that we do is we have to change our limits. Okay. The second thing that we have to do is when we evaluate, do not go back to terms of x. Okay, so now what I want you to do is pause the video, work number 2 on your own, and what I'm going to do, instead of recording the whole problem, I'm going to write down the answer step by step. So if you want to try working on your own, if you get stuck, then play the video and see it and watch it step by step. Okay, once you get to this stage, I found my u, my du, and I changed my limits. So one thing that you'll notice here with this problem is that these limits of integration have now been flipped, and that sometimes happens. So in the original problem, we had from a to b was 0 to 1, which is fine. But then those flipped and became 1 to 0. So if your, when you do this, and your lower limit ends up being higher than your upper limit, then all you have to do is make the integral negative and then switch the limits of integration, just like we've done before. So then this negative 1/2 will come out, so this will actually become a positive 1/2 out front of the integral of u to the 1/2 du. Okay, go ahead and finish that up. And as you can see, this one was very easy to evaluate. You end up just getting 1/3. Okay, so again, I want you to do the same thing with example 3. Work it out on your own, pause the video, and play it when you get stuck or you're ready to see the answer. Okay, so here is u du, and you see that this one is one of those that you're going to have to solve for x, and then change your limits, and this is what you should have before you simplify. So now go ahead and simplify, pause the video, and I will pause at my next step after I've simplified, but before I take the integral. Okay, so here's the integral before, after it's cleaned up, but before I integrate. So now go ahead and integrate and evaluate and get your final answer. All right, and so there's your final answer. Hopefully you're feeling better about that. So we're going to look at a couple of different types of examples using this property. Okay, example 3 is actually what I did at the very beginning, just worded in a different way. So I have, I want to express the integral from 3 to 4 of f of x minus 2 in the form of the integral from a to b of f of x. So you can see that I'm doing the same thing here. I don't know what my function is. At the very beginning, I made my function be x squared, and then we shifted that 2 spaces to the right. So this is essentially what we're doing here. All we're doing is, this is the function of f shifted right 2 spaces. All right, so if you were to want to now put this in the form of just f of x dx, so without the shift, then from what we did at the very beginning, this makes sense, but I just want to reiterate it one more time. So if u is x minus 2, then du would be dx. So then we need to find our limits, our new limits. So u at 3 would be 1, and u at 4 would be 2. So then we would rewrite this as the integral integral from 1 to 2 of f of u du. And just because we have the u's now, if I now change my whole problem, this is really going to be the same as the integral from 1 to 2 of f of x dx. Since you have this u and u here, it's okay, you can make those into x's as well. Okay, so that's just really the same thing that I went over at the very beginning. Okay, so for our last problem, we have a little bit of notation to talk about here. So if capital F prime of x equals g of x, find the value of the integral in terms of just f, not f prime. So if you see here that I'm given the integral and that's involving g. So let's go ahead and just dive into this using u substitution, and then we'll talk about how the notation of the f's play into it. So if I were to evaluate this integral, then you would have this inner function here, so that would be u equals x squared plus 5, and du equals 2x dx. I've got the x dx piece, and so then the x dx would equal 1/2 du. Alright, so I also have my limits of integration that I need to change. So then u at 3 would be 3 squared plus 5, which is 14. And u at 7 would be 7 squared 49 plus 5, which would be 54. So now this would be equal to the integral from 14 to 54. And that x dx, that becomes the 1/2 du. So we have g of u times 1/2 du. So then the 1/2 will come out front, and we get this expression here. Okay, so if I know that g of x is the same as f prime of x, then I could really make this be f prime of u here. So when I take the integral of f prime, then we end up with regular capital of f. So this will be, and remember this is not the second fundamental theorem of calculus where we're taking the derivative of the integral. This is the first fundamental theorem of calculus, which says when I integrate a derivative, then those are going to be canceling. And so what you're left with is the 1/2. And then first fundamental theorem of calculus just states that would be f at my upper limit minus f at my lower limit. And so now you have everything in terms of that capital F only. Okay, the last thing that I just want to mention, I'm not going to do any problems with this, but I'm just going to mention some properties of integrals. So if you have an even function, so an even function would be like x squared or x to the 4th. What that means is even is reflective across the y-axis. All right, so you can fold the function across itself on the y-axis, and it ends up being exactly itself. So what that means is if f is even, then if I take the integral from negative a to a, so let's call this negative a and this a, what that would represent would be this area and this area. Then you can see geometrically that the integral from negative a to a is equal to 2 times the integral from 0 to a of f of x. Okay, so that's pretty common sense. Where that helps you in evaluating is now instead of having to evaluate at this negative a, you can evaluate at 0, which is a lot easier to do. Okay. Then also we have the odd functions. So an odd function is rotationally symmetric. So if I rotate this 180 degrees, you map onto itself. So same thing, if I find the integral from negative a to a, and I calculate that area, so since this is symmetrically, rotationally symmetric, then I have negative area and the same value of area in the positive. So what's going to happen is those two are going to cancel out. So that also is very helpful. If you know that a function is odd and you're finding the integral from negative a to a, then the area is going to be equal to 0. So those are just some properties that you need to keep in mind when you're solving integrals.